Thanks, Michael. I'm super excited to be here, and I'm happy to make this interactive. I know also my own background is probably quite different than some of yours in the audience, in the sense that I primarily do machine learning and artificial intelligence. So if I use a term that you're not familiar with, just feel free to raise your hand, or if you think, I know what that is, but that means something very different than what it sounds like she means it to be, just let me know. So if you look at the news right now, probably almost any day you look at the news, there's some article about whether AI is going to automate humans. And is this going to happen that we're going to automate things like being able to do skin cancer detection? Are we going to automate taxi drivers? Are we going to automate drone flying? And what is that going to be, and what sort of implications will that have on society and the workforce? And really, a lot of the history of artificial intelligence has been about making artificial humans, and in some ways thinking of maybe not explicitly trying to replace humans, but really trying to make agents that can do anything that a human can do. So sort of trying to replicate human abilities. But I think of artificial intelligence in a quite different way. So who here has seen The Matrix? Okay, so you guys might remember the following clip. Let's see if this will work.
Can you fly that thing?
Not yet.
Operator.
Tank, I need a pilot program for a B-212 helicopter. Hurry.
Let's go.
So this is probably exactly how your own educational experiences have been, that you want to learn something and you just download a program into your brain and then instantly you can do the thing that you wanted to do. Of course, that is not what we actually have right now in terms of education. Education is mostly the same as what it's been for 100 years. But I think that this vision, the reason why I often show this clip of The Matrix is because I think it's a really inspiring vision of what technology could enable us to do. It's demand-driven education, it's real-time, it's incredibly fast, and it's exactly targeted to what the user actually wants to learn. And so I think it's this really amazing vision of what education could be and what lifelong learning really could be. And Kentaro Toyama, who is a technologist who thinks about information communication technologies for international development, talks about technology being an amplifier. It's an amplifier of sort of existing things in society. And I think that if we think of artificial intelligence as being an amplifier, that to me is a much more exciting goal than thinking of artificial intelligence as being a replacement for us.
Can you fly?
So in the work that I do, I come from a background of thinking about an area called reinforcement learning, which a number of people may have heard about. And in these sort of scenarios, I think of an agent that's trying to help a human do something or augment the human's own capabilities in sort of a loop-like process. So we might have an agent that's represented by the computer here that is feeding a math exercise to a student. And then the student responds in some ways. And then periodically we might get some sort of reward signal that indicates how good is the way that the computer is teaching the person. So maybe we can see whether or not the student has passed an exam. And there are really important questions around here of what should that objective function be? You know, is it that they pass an exam? Is it that they play our educational game for 5 more minutes? Or is it whether they choose a STEM career? So there are a lot of different choices there about what is it even that we're trying to optimize for. So when I talk about reinforcement learning, we often talk about a policy, which is a mapping of past interactions to the next activity. And a lot of our goals in reinforcement learning can be viewed as how do we construct some way that our agent should make decisions to maximize reward. So it should be a strategy for saying, depending on how the student has done so far, what is the next math exercise to do? So that over time, we're going to optimize our reward. And it turns out that this comes up not just in education, but in many different other types of domains. So we're also thinking about healthcare examples in this situation from a similar modeling framework. And in these cases, you could think of, let's give some sort of medication dosage suggestion, and then we observe blood pressure. And maybe there's some penalty if the blood pressure is too high, or maybe there's some other aspects about side effects. And we're trying to figure out a strategy for how to provide drug dosages over time. So we can think about this in the context of healthcare. And we can think about this in the context of consumer modeling and marketing. So there are many different types of domains where we have kind of this interactive process, where we have an artificial agent that could be interacting with a person and trying to optimize something through a series of interactions with that person. Now, in general reinforcement learning, we call that first thing we're doing, whether that's picking a problem or picking a treatment suggestion, as an action. And then we get some observation back, and then we have a reward signal. So we can have this generic framework for thinking about this sort of continual process of an agent selecting actions and then getting some observations. And so who here has heard about the recent results in Go and Atari? Maybe not everybody. So there's been some really exciting progress recently. In video games like Atari, you can now get human-level performance by artificial agents, and those agents are typically using these type of reinforcement learning algorithms. And similarly, in the game of Go, we now have exceeded human-level performance with Go, and a lot of the ideas come from reinforcement learning. And again, in robotics, this is one of Google's arm farms. It's an arm farm because you have many robots with a single arm doing something. And there's a lot of interest in how we can use these types of techniques in robotics as well. But as Michael mentioned, one of my primary interests is thinking about how these sort of techniques apply when there's a human in the loop. And so instead of there being a video game we're trying to play, we're trying to help someone learn math, or trying to help a patient have a higher quality of life. And people are not the same as robots or video games. And of course, they're not the same, but they're not the same in a couple important ways that change the type of techniques that we need to develop. So in particular, in the context of video games, it's often fairly cheap to try things out. So I can have my agent fail to succeed at Pong or some of the other Atari games for on the order of 200 million steps. And that is not a hypothetical number. That is a real number. So you can do that, but that's really computation. So we could simulate that for like 12 hours, sometimes more like 2 weeks. And then we could have an agent that learns to play these games really well. And then we often report the final performance. So now we've got an agent that plays this game really well. So it's often cheap to try things, or it's pretty easy to simulate. So we don't have perfect models of the physics of the world, but we can do pretty well. So we can, in these sort of robotics examples, we can often write down pretty good simulators of how the world works. And then we can try to use those to, say, construct a policy for how to grasp an object. When we think about people, it's quite different. So people, I would argue, are high stakes. I don't want to make a tutoring system that only learns to teach people fractions after I have not taught 1 million people fractions. So it's high stakes. The data I'm getting is from really interacting with people. And yet they're also really hard to model. So we don't have really good models of student learning. We don't have great models of human physiology. And so we're not really in either of these two camps, which are often explored in reinforcement learning scenarios. And so what I'm going to talk about today is sort of some of the technical challenges that come up when we're trying to do this human loop reinforcement learning, and also thinking about some of the things that we do have access to in these type of domains that are really people-focused, and what are the sort of technical challenges that come up there, and what can we do? So let's imagine that we're in the case where we have a set of classrooms called the A classrooms. And in those classrooms, the students first got to do an exercise on a computer and then an exercise on a chalkboard, and they got a score of 95 on an exam. And then I have this other set of classrooms called the B classrooms, where they did the opposite order of the activities. They first did a chalkboard exercise and then a computer exercise, and they got an average score of a 92. And then you have a new student who walks in and says, okay, what do you want me to do? We want to pick something that's going to maximize the score. So if we did this, what are the questions? Well, first of all, what would you do? Or what are the questions we'd need to ask in order to make this decision of what to do for a new person? Yeah.
But what's the difference between the students in classroom A and B?
Right, so it might be that classroom A is kindergartners and classroom B is you guys, and so, or maybe I should say the opposite way around given the scores, and so there might be some really big differences in the types of students in A and in B. Is there anything else that we should maybe ask?
Yeah. how many students were in each classroom.
Right. So if it turns out that this is, classroom A is Michael and classroom B is me, then maybe we can't really generalize from that to what we should do for all new students. Another thing that people sometimes suggest when I bring this up is, well, is that test really actually even a reliable indicator of whatever it is they're learning? Like, let's say they're doing math exercises here, and this was a history test. Maybe that tells us nothing about what we should be doing. But yeah, all of those considerations. So what is the differences between these groups? How many people do we have? And is this a reliable indicator? Let's imagine this is a reliable indicator. This is really a math test. That was really math exercises. So this challenge of doing kind of this counterfactual reasoning of saying, what should we do? What can we generalize from our past experience is a really foundational one. And it comes up in many domains. So imagine something like maintenance scheduling. We're doing a collaborations with Siemens right now. So you might see there are different orders of when you could do maintenance or when you could get your oil changed or things like that. And you want to optimize for that. You want to sort of optimize cost over time, and you have old data, and you can see what the outcomes were. And similarly, in the case of healthcare, often now with electronic medical record systems, we're going to have sequence of treatments that are given to patients, and then we can observe their outcomes. We can observe, how well are they doing, different measures of sort of quality of life. And what we'd like to be able to do is use that information to try to make better recommendations for future patients. But why is this hard? Well, it involves this counterfactual reasoning. And there's this really lovely talk by Judea Pearl, who's sort of one of the founders of causal reasoning, at least in computer science. And he argues that our ability to do counterfactual reasoning is really a core aspect of what it means to be human. We can imagine things that we haven't observed. And so we have to do that here because I didn't tell you what would have happened in the B classrooms. Like if those B students had gotten, the B classroom students had gotten this other intervention, the same one as in the A classrooms, we don't know what would have happened. We can't observe these parallel universes. We can only observe a subset and we can't rerun it. The second challenge is generalization. So here we only have two types of things we can do. We can either use a computer or a chalkboard, and we can think about which order we do that in. And so there's a very small number of possibilities. But if you start to think about all the drugs that you could prescribe, all the different types of medical interventions, and also not just doing this for 2 time steps, but for many time steps, there's a huge combinatorial explosion. And we don't want to try all of those. There's probably not time in the universe to try all of those. And so we're going to have to be able to generalize somehow from our previous experience to try to say, okay, would it actually be better to use the computer twice? So in general, this issue of saying we do have access to some old data, sort of the data about decisions and their outcomes, and we want to use it to make better decisions, can be framed as follows. We're often calling this batch data policy selection. And again, when I say policy, I mean this mapping from, given a scenario, what decision should we do? So in this case, let's say we have this old data and we have a bunch of different policies we could consider. These could be constructed using reinforcement learning. They could be from experts. They could be done in different ways. And then we want to evaluate each of them. So we want to say how good, given our old data, do we think each of these strategies would be if we were to use them in the future? So should I teach my students using the first thing or the second thing for all future students? And how good do I think that'll be, let's say in terms of their test scores? And then I probably want to do some sort of policy selection at the end and make actually a decision about which one to then go try with my students or deploy in the hospital, etc. So I'll just give a little bit of background. My original interest in this came from an educational game that we were working on a few years ago. This is in collaboration with Zoran Popovic, who is a professor at the University of Washington. And this is refraction. I think it's been played by around 500,000 students. And it involves splitting laser beams using fractions to try to feed spaceships, fuel them up. And we had data from the past, and we wanted to figure out, let me see if I can play a little bit of it here. Let's see if the video works. So what the student can do here is they can split this laser beam, and then they can sort of fuel the spaceship. And what we wanted to figure out, there are different levels which involve different fractions and different types of spatial configurations of different levels of difficulty. And so we wanted to be able to order these to keep people engaged in learning. So in this scenario, The policy we're looking at is sort of some model of player state, some history of the previous levels they've done and what they've done in those levels, and deciding what the next level to give them. And our goal was to maximize engagement, which is just how many levels do they play. Now you might argue, is that really the right optimization criteria? Really, we're going for learning, and the idea here is this is sort of a game that's online, that there's no constraints on people using it for a long time, and people generally use this for the order of somewhere between 4 to 6, 7 levels. And we wanted to increase how long they were using this, with the idea being that if this is a pedagogically effective game, then that should also hopefully help them learn more things. And the old data that we had was from about 11,000 students. And one thing you could imagine doing in this case is building some sort of statistical predictive model. So what I mean by that here is we're just going to build a model that says, if I'm in this, if the student has this here series of historical interactions with a game, and then I give them a new level, how well are they going to do in this level, and maybe what they're going to do in this level. And the reason we might want to build the statistical model is because then we can use it as a simulator. So now, like I talked about before, how in robotics, there's often these great simulators of what it's like to move a robotic arm. Now we have a simulator of what it's like to be a person playing this game. And so then we can try to just use reinforcement learning to try to optimize a policy for if that's really the right model of a person, what is the series of levels we should give them to keep them engaged? But unfortunately, there's some problems with this. So the model might not be good. I told you before that models of people are hard. Even with deep neural networks, they're still hard. And so 11,000 data points is a reasonable amount, but it's not huge. And so we're probably not going to have a perfect model. So if we have a bad model, we know from our theoretical results that we can get a bad estimate of a policy. So if I pick a particular strategy for how to show levels to a student, and then I use my model to estimate how many levels that student will play, my estimate just might be wrong. Might be off. And that seems sort of reasonable, right? Like it seems like if we don't have very good models, we can't use them as very good simulators. Here's what's worse. More accurate models can lead even poorer performing policies. So now it seems really bad, right? Like I already told you, well, if our model's bad, we're going to be in trouble. But now I'm saying, actually, even if your model's good, you might still be in trouble, which seems really bad, right? And so why did this come up? This was sort of an interesting issue for us when we started. So on the x-axis here, you don't have to worry about the exact details of the representation we're using, but essentially these are just a line about more complicated models. So on the right-hand side are really simple models, and on the left-hand side are still pretty simple models, but a little bit more complicated. And we're looking at two things here. So the gray line is log likelihood, which is on a held out test set of our 11,000 data points. So let's say it was a 1,000. I don't recall the exact number, but let's say it was 1,000. We built a statistical model and we saw how good was our model at predicting what people would actually do on that held out test set. So this is a measure of how accurate is our statistical model of player behavior. And what this is saying is that gray line is going up over time, which is saying it is better to have a slightly more complicated model. We are better able to model player behavior if we have a more complicated model. Okay, but then what's the black line doing? The black line is saying, okay, if you take that model, you pick the best policy that is optimized for that model, and then you run it in the real world, or so we're actually using an offline estimation procedure, but we actually evaluate how good that would be, and it's getting worse. So if we use that model and then try to get a good strategy for how to map level, student state to levels, we're doing worse over time with more complicated models. And why is that? So this was sort of confusing to us for a while, and then I think it's a really interesting issue. So the issue is these models, these statistical models, are just looking at predictive accuracy. So what do I mean by that? Well, let's imagine that you're trying to build a robot that can make tea. And the robot can see everything in the kitchen. It can see the outside where there's a sunset, there's a kettle, there's steam. And it's trying to use all of those features to figure out a policy of, okay, given I see the sunset and the stove and the steam, do I take the coffee pot off or on? And it turns out the only thing that you need to care about there is whether or not the water is above 100 degrees or not. Doesn't matter about the sunset, doesn't matter about, whether there's a lot of steam or not. You just care about whether the water's hot enough in order to make your steaming beverage. And let's see if I can get this back up. And the problem is that if you're building a predictive model, it's going to try to model the sunset, it's going to try to model the steam, and it doesn't know that all you really care about in terms of making good decisions is whether your water is hot enough or not. So that's the problem, is that you kind of have a mismatch of objectives here. What we really want is a good policy that's going to allow us to make good decisions. What we're optimizing for here is predictive accuracy. And so there's a disjoint. And so what this led us to say is, okay, we don't necessarily want to first kind of squeeze our data through this thing of trying to get accurate models of player behavior. We really just want a policy that's going to allow us to get high-performing results, helping our students get engaged. So as I mentioned, just to summarize that point, a lot of the prior work says if the model is good, the policy is good. The problem is that the model class you're using and the features you're using might be wrong. And so particularly if you have small amounts of data, you might be very misled in the way that we were here. And it's very hard for us to know if our model type is wrong with finite data. And this actually relates to a lot of other challenges that are coming up right now. In robotics, people often call this the simulation to real problem, that you've got a simulator that is not perfect. You don't necessarily know how it's not perfect, so that when you deploy your resulting policy and your robot fails to grasp, how do you know what went wrong? So we wanted to do something that was robust to kind of this model class mismatch and this objective mismatch. That what we really care about is trying to get a good policy out, a good way to help people learn. And so we use a new statistical estimator, the importance sampling estimator. And what it does is it gets a direct evaluation of a policy's performance. So there's no modeling of player behavior at all. We just try to directly estimate how good is this policy. And the idea, for those of you who may not have seen this idea before, or as a refresher, is that we had sort of some distribution of student outcomes before when we used our previous strategy. In this case, it was just randomly selecting levels for the student. And then we want to kind of reweigh those to look more like the distribution of outcomes we'd get under the alternative policies. So when we did this, we found that we could get a 30% higher engagement than what we saw before. And this was significant for two reasons. The one was that we could accurately predict this before we tried it in the real world. So that was showing that the statistical estimator was really a good prediction of how well we were going to do, unlike the models. And the second is that there was room for improvement, that we could use these type of reinforcement learning algorithms to get a lot better results. And I think the intuition for that is that it's hard to write down what level a student might do at each point in these cases. There's a lot of things students are doing when they interact with this sort of game, and so it was hard for game designers to figure out exactly what that mapping should be. And that's exactly where optimization and data might be helpful. Now, in general, this technique of importance sampling can be high variance. The estimator can be quite inaccurate and vary a lot, and its variance can grow with the number of decisions that are made. So I mentioned before that this previous game, people would only play it on the order of 4 to 6 levels. In some of our other educational settings, we're making many more decisions. So students are using our tutoring system for 20 problems to 120 problems. And so in those sort of settings, it can be much harder to do this sort of estimation. And so we've been working on a lot of different technical challenges that come up with that. So this has been a general big focus of our lab, is how do we make, how can we use old data to try to get better policies for the future use, both in education and also in healthcare. And as we've gone through this, we've discovered some surprising things. So it turns out that sometimes you can have statistical estimators of how good a policy will do, both of which are unbiased, which means that or just as a refresher, that means that whatever estimate you get of how good the policy will be really is centered around what its real value will be. And the problem is that then when you make decisions about that, it can turn out it's still not fair. And that's because sometimes you're going to have much more variance in one estimate than the other. So when you're finally trying to make a decision about which thing do I deploy in the future, you can be systematically biased against the better solution. So we had a Best Paper Award for that last year, and I think it's a really interesting technical issue because this stuff is used in a lot of robotics problems and a lot of other areas of reinforcement learning. So we're continuing to do a lot of this work, and I think that there's some really interesting questions here about how can we do this, particularly in these cases where it is really hard to model people. So the second thing I want to talk about is expanding the space. So one of our other tutoring systems was this Histogram Tutor. Histograms can be thought of as a precursor to understanding basic probability and statistics, and they tend to be really confusing for people. So things like knowing what is on the y-axis of a histogram are often really confusing when you're first learning about them. And we had this vision of doing this continually improving tutoring system that was getting better and better the more people it would teach. So, the student would be doing problems selected by our tutoring system. The student would be getting them right or wrong. At the end, we'd do a post-test. And based on all of that data, our system would automatically change how it taught people, and it would just get better and better and better. And so it would be improving across many, many students that were all having this interaction process. And the problem was that over time, the tutoring system stopped giving some problems to students. So there was a series of about 8 skills here that we were teaching, and about 6 of them stopped being taught. So that was a little strange because we were actually trying to teach histograms. And then this kind of gets back to this issue of what is the reward function? What are we trying to optimize? And what we were trying to optimize in this case, just to briefly mention, is we were trying to look at essentially post-test. So sort of how good did they do at the end, divided by the square root of the number of problems we gave them. So what we were doing here is we were saying, well, we want to kind of trade off between learning effectiveness and learning efficiency. And so we want to have them do really well, but not require, if they can do really well in 10 problems instead of really well in 50 problems of practice, it's better not to waste the student's time, so we'll give less problems. And the problem was that it just didn't give any problems for a whole bunch of skills. And so somebody have a hypothesis of what had happened there? Why given that objective function? I know it's right after lunch, but everybody's probably in need of coffee too. But does anybody have any idea why, given this objective function, it might stop teaching some skills?
Those skills were not post-test.
Yeah, so one thing would be maybe those skills weren't on the post-test, which is a great question. In fact, they were all on the post-test. So all the skills were on the post-test. If they weren't, then that's certainly, yeah.
You give no problems, you have infinite improvement.
So that's a good point too. So we did correct for that. So that's a great question. If this here strictly, it would be 0. We did make a slight change to that, so it wouldn't be, but it's exactly along that line. So what would happen? Okay.
It tries to give them problems that like the easier problems because it wants them to get a good score. So it sort of avoids the problems that people tend to miss a lot, which are probably the skills you're trying to teach.
Yeah, so that definitely could happen, and all of these ideas are really great. In fact, ours is even simpler than some of those suggestions. The idea was that the post-test score didn't change whether or not we gave them any problems. So if it doesn't change, you just don't give any problems because you're going to minimize the bottom. So if the top is a constant, the best thing to do is to give as few problems as possible. And it's a little bit like if you go to lecture a lot and you realize the lecture isn't helping you learn. I'm sure you've never had that experience. And so in that case, you just start to skip lecture. Or you realize the textbook doesn't help you learn and you stop reading the textbook. So what the system had basically self-diagnosed was that our beautiful content that we had spent hours creating was completely ineffective at helping people learn for some of the skills. And so it self-optimized. It was like, I don't need any of that. The students seem to do the same on the post-test, whether we give them this content or not. So we'll skip it. So this was, perhaps slightly a failure of our curriculum. But I think at a high level, it introduced this really interesting issue, which was it can self-diagnose that something's wrong. And so there's 2 levels of self-diagnostics here. The first is that none of our material is being taught, so that was good to know. But the second is that it couldn't reach the performance we expected it to. So we were expecting that if we gave the students the right amount of problems, everybody would do well on the post-test. And what it was finding is that, let's say maybe, everyone was getting like around 70% on the post-test, regardless of how many problems they did. And so people just didn't learn the material. It wasn't that everybody had already understood it, they just weren't learning. And so if you as a human know how good you want your system to be, you can realize there's a gap there. And so the system says, I'm done optimizing, and there's still a gap, which means something needs to change. Now, in the context of sort of classical reinforcement learning, you'd be stuck. Can't do anything at this point because that's your system. And you've optimized as well as you can, and it's at 70%, and you're just done. But of course, as humans, that would be very, very sad if that was the case. That would mean things like the Zika virus comes along and we'd be like, well, that's too bad. We don't have a virus or a vaccine for the Zika virus, so guess we're stuck, but we don't do that. We invent new things all the time. Like we encounter new problems for which we have no existing solution, and we invent something. And in the context of reinforcement learning, that would be called inventing new actions. So we see that we are stuck and we invent new things. And similarly, there are times where we realize we don't have the information we need to be able to make the type of decisions we need to. And so we invent new sensors to try to sense new things, like the Hubble Space Telescope. And so why can't we have that in the context of these sort of human loop systems? So this, again, is a big distinction because, in playing Go, I can't suddenly decide that I'm going to use a new move, which is like take all of the other person's pieces or to declare victory, right? We can't do that in those sort of closed systems. Same in Atari, right? I can't suddenly teleport my agent to the final room. But we can do that sort of thing in a lot of human-facing applications. We can invent a radically better patient treatment. So in thinking about this in the context of human loop reinforcement learning, we want to augment the system so that it's no longer this kind of closed box, but we can have outside input. So the first thing we started thinking about is, well, how could we have an agent reach out to a human, maybe an expert, maybe a crowd, and say, hey, I've optimized as well as I could, and everyone's still only at 70%. What should I do? Like, I need another video to explain histograms, or I need another problem. Can you help me out? But we wanted to do this in a way to kind of direct the human effort. People are busy, and we'd like the system to say, all right, well, given my optimization of this system, and where I think people might be failing to learn, or where I think the system is currently doing poorly, can you add something exactly there? So the way we did this, just to briefly sort of give some of the equations, is that we tried to think about the local improvement we could have. So imagine that there's some situation where the student isn't understanding something, and you could introduce the perfect explanation. How much of a difference would it make? So we tried to quantify that, which requires us to have some upper bounds on sort of how good it could be if we were to add this new action. So can we imagine sort of introducing the perfect vaccine for Zika virus? Or could we imagine sort of introducing this perfect explanation in how student learning would go later on? And one of the challenges that come up when we do this is that this is all during the process as the system is itself optimizing. And so often there's a lot of uncertainty in terms of how the system is currently performing. And so one of the things that we came up with is to say, don't add in actions in places in the world where the existing action might already be good enough, and you just don't have enough data yet to tell that. Add in actions in the places where you have a lot of evidence that you are not doing well. So like if I've just given one lecture in the class on a topic that's really hard to learn, maybe that was a good lecture and we just need some more practice with that. But if I've given, this lecture to 30 classes and nobody ever understands it, then it's probably time to do something new. So what we did to try to check how well this worked was we did some different simulations. This is kind of a sort of completely toy domain, and the idea here is to say, well, what if there's a really large action space? Can we kind of grow over time to add in these new actions and get good performance? And the idea is that this sort of directed way of asking to augment the space and get better actions for your agent to select from over time is better than either doing something where you just get random actions or where you try to think of things that are just like frequently visited. So you could imagine just saying, well, what are lots of places where people get stuck? Is that the right place to add a new explanation? Or you could do it in this more targeted way, and the targeted way is better. And another thing that I thought was interesting, again, this is in simulation, but we tried to say, well, what if the advice you're getting from the human when you ask for these new ideas is not always good? So sometimes, maybe like I try to think of a new lecture and it's bad, and that is not effective. The nice thing we can find here is that the system is still learning about what actions are effective or not. So as long as some of the new actions that are being added are helpful, its performance goes up over time because it can learn to discard the bad suggestions. Yeah.
Why is it going up even if random?
Because in this case, some of the actions, the random here is just how you're selecting where to add in those actions, and some of them are still good.
So if I'm adding lectures randomly, I'm still improving my education?
As long as some of the lectures you're adding are good.
Okay.
Yeah. So then, and I'll return to this example later, but and so then we started to think about how could we do this for a real educational setting. This is, again, a game that was developed by Zoran Popovich's lab, and this is math word problems. And the idea is that we often, in many tutoring systems, we give students hints. And these hints themselves can be thought of as an action. And they're not always very good. They're written by game designers or the people the researchers involved, and sometimes they're good and sometimes they're not so good. And so we thought that we could ask people to figure out, to add in new hints exactly where we think it's not currently being very effective. And I'll return to this example in a sec. So another thing that we thought about in this case is, well, all right, maybe the action space is good, but maybe we're missing something. Maybe there's something about the student or about the person that we're missing that would allow us to make better decisions. So for example, maybe I'm talking to a student, or maybe, and I realize halfway through the discussion that maybe they don't actually know algebra. And so then if I ask them, do you know algebra, then I can provide a much better explanation than just assuming that they knew algebra or just sort of trying to pick the best explanation regardless of whether they know algebra or not. So it is often the case that additional features allow us to make better decisions, but there's a lot of reasons not to put in all possible features in advance. It tends to mean that we need more data to learn a good policy. So our idea is to think about whether we can do this strategically. Can we think about this in a utility-driven way? If we were to add in a new feature, could we make better decisions? So this is something ongoing work with my grad student Ramton. And just as a really small example, some of you guys might have seen these before if you've taken AI. This is a grid world. It is a very small toy domain that we often think about in AI. And in this scenario, it's only those big black boxes, which are kind of the state of the world. So there are 9 states in the world. That S means a start state, that G means a goal state, and you have basically a little robot that's trying to learn how to traverse. And the thing is that this is the world that it sees, so it only sees like those 9 states inside of the big black boxes. But in reality, the world is very complicated, at least more complicated than that. There's things like rainy states and windy states, which cause its dynamics to move in different ways. And so the real policy can depend on more distinctions than it currently has access to. And so what Ramton developed is an algorithm that tries to adaptively split the state space and refine things based on utility, based on the idea that it uses its data, it hypothesizes whether or not there could be additional latent features that would allow it to make better decisions. If it thinks it would, it splits. And that's sort of simulating asking a human, hey, I think there might be an additional feature here that if I knew it, I could make better decisions. Can you help me out? And one of the interesting things we found here is that the number of distinctions it was making was still smaller than if you had split the entire space. So you may not need to make all the distinctions in the original domain. Yeah.
People are not that good at this. Like, metacognition is hard to say. Like, oh well, if I only understood like this concept, because you may not be aware that that concept exists. So, how do you know what you don't know?
Yes. Yeah. No. I think it's a really interesting issue, and I will also get back to that when we return to the word examples. So at a high level, our vision here is to say, how can we use this human expert or a crowd to try to make the system better, to change the definition, the spec of the system, if you will, over time, so that we're getting the system that's not only self-improving, but is kind of expanding in scope to try to really achieve the performance we want. But as Michael just mentioned, including humans loop has some limitations as well. So, well, let me first just talk about sort of the more grand scheme, and then I'll get back to that. So this could be used in other ways too. This could be used in crowd work. So this is some work that with my student Cheyenne Durruti and then our collaborators Eric Horvitz and AJ Kumar. And in this case, we were thinking about crowd work tasks where we would like to train people to be able to do more complicated tasks. And one of the challenges in this case is that we may not know what's the right way to train them to do more complicated tasks. And it also takes time to write those sort of instructions. And so we were curious about whether we could have a scenario where, because we know that worked examples are often helpful, could we take the solutions that people are generating and use them to train the crowd workers? So we published this in Kylie a couple years ago to show that, yes, you can use sort of the old solutions to try to bootstrap and teach future people how to do this task. And in general, you could imagine sort of a whole ecosystem where if you're doing a complicated task, you also need to be able to validate and grade the solutions that people are generating. And so you could be using the crowd both to create solutions, use those solutions to train the crowd workers, and getting the crowd to validate those. And the thing that I think is interesting about this type of vision is saying, well, really we could be using machine learning to try to kind of select which solutions are effective for teaching. Those might not be the same ones that are actually the best solutions. There can be differences between how you want to demonstrate and how you want to teach. But that we could sort of have this closed loop system here, which is leveraging both people, particularly for the invention of the new content, and machine learning to try to refine it. let's get back to that issue that Michael was just mentioning about metacognition. So we haven't looked at that issue in terms of the feature splitting, but we have looked at some limitations of asking people for actions. So a lot of work right now in reinforcement learning and robotics and AI is thinking about this issue of learning from demonstration, where you have someone demonstrate an expert, like how to pick up a cup, or many different types of aspects, particularly in robotics. But teaching is not the same as doing, and this has been noted before. And it's not clear always that learning from demonstrations is the best. And teaching might be much better, but people might have challenges. So teaching is really hard. And if we looked at what was happening in this case, so we had education students who were providing these hints to the machine that then were being used to teach later students. So you can think of the system, which is this math word problem system. Periodically, we ask education grad students, hey, the system isn't working very well. Could you provide some new hints that students can use to learn? And then we keep going. And the problem was it made no difference. So it didn't seem like the system was really getting better over time. And when we dug into this, we realized it was really hard for people to know what new hints to provide. And I think it was hard from a couple things. Even though they're general sort of education experts, they're not an expert in this particular subgame, and they're not the same demographic as the people playing this particular subgame. There's a lot of delayed feedback about whether or not how they were teaching the agent was effective or not, because it takes a while to assess that, just like in a lot of teaching, whether or not you're being effective. And we weren't doing any training of people to try to help them do this. And so, when people are sort of teaching or thinking about how to teach another person, I think we sort of want them, in this case, to be able to think about what is the robot doing or what is the agent doing, and what is the task involved, and how can we help train the trainers? So we can think of the humans training the machine in this case, but we may need to educate and train the trainers in order for them to be able to provide effective feedback. And I think as we start to generally think about this closer interaction between machines and humans and sort of these more collaborative aspects, it's going to be really important because there will be many people interacting with machine learning algorithms that are not machine learning experts, and allowing to train them to provide effective feedback and labels and interactions with the machines, I think will be really important. So just to summarize, I talked a bit about how do we learn from the past to try to decide the future. I talked about how we could maybe expand the space of actions and observations in order to make systems that can outperform their original specifications. And I also talked a bit about how I think we're going to need to change some of the interaction between human and machine learning in order to get truly effective systems. I just want to thank my group and open it up to any questions.
We have some time for a discussion, feedback, questions, suggestions of new actions she could take.
Have you thought at all about learning reward systems and like what motivates somebody to play a certain type of game versus not? Or yeah, I don't know.
So I think the question of learning reward systems is super interesting. I think in particular, to go back to the beginning, it was Trinity who wanted to fly a helicopter. She had a particular goal. And I think ideally we'll make all of these systems where we could sort of expose people's reward or objectives and then support them towards doing that. I think in our own work, we've normally been in situations where we've imposed the reward structure, like post-test performance or engagement. There's certainly a lot of interesting work on preference learning, where you try to infer, say, from people's actions, what their reward function is. Or sometimes it's called inverse reinforcement learning. You try to infer their reward. But I think that's a really interesting issue. I also think there's a really interesting issue, particularly in the context of coaching and training, of how do you grow someone's reward function? Like, I think there's often this challenge between saying, this is maybe what you currently want, but maybe you're not aware of these other potential outcomes. And so like a good coach or a mentor often exposes you to additional opportunities that then you decide you incorporate as part of your goals.
This is not well formed yet, but I'm trying to reason through, like in our educational system, often there's a lot of value placed on keeping someone within the system. So maybe you're struggling to learn math, well, let's keep you around and put you into a different math lane or something so that you stay around. And that seems to be optimizing for some sort of reward criteria that might be different than if we were just saying try to maximize the amount that they've learned or something like this. Because or subject to budget constraints, like which might do what this thing did and say, oh, okay, we need to cut them out of the system, they're not learning math. And this feels to me like it's, I don't know which one's better, although I have a hunch, and it seems like part of this is about the formulation of effective reward strategies. I'm wondering, as we're moving into these more sort of socio-technical domains, how do we reason about what are these rewards and when are we going to end up with these sort of myopic outcomes and when not?
Yeah, I think it's a really interesting issue. I guess a couple thoughts within that. So one thing that I find interesting in terms of how people use these actual systems, so a lot of these sort of more personalized systems, you can also skip people ahead. And in terms of keeping people coherently within a class, it's really hard to teach people, of which some people are in Unit 1 and some people are in Unit 20. And so people often get caught up, which means they're just advanced. And so maybe like at some point, you're struggling, you're still on Unit 1 of pre-algebra, but everybody else is now halfway through algebra and your teacher just moves you up, and they observe that empirically a lot. And so people aren't necessarily following these personalized systems always because it is really hard in the classroom to have people being that disparate. It's very hard teacher load. I think in terms of maybe the second thing of saying like, what is the reward function? I mean, I think another big issue, like if we look at the sort of the No Child Left Behind, the objective there is that maybe everybody passes, gets to a sufficient level as opposed to optimizing the expected outcome. So maybe that's going to be a little bit lower. And I think there's a tension often between saying, can we have constraints that make sure that you make guarantees for the individual as well as sort of improve the average or improve the expected amount. I think ideally another thing too is that you would like society to sort of explicitly decide this is the longer term objective, which is probably not just passing this year's test. And it's like, reducing crime rates later, getting into college, having long-term jobs. And the problem right with that is having these very long-term data streams in the credit assignment. There's been some really cool work looking at tutoring system work and then in like sort of 8th grade and later STEM career choice in college. So when we have those data sets, I think that's really exciting because those are really the outcomes we would like. I don't know if that answered your question fully, but
yeah, I mean, I think it's the kind of space that I end up having to navigate in many different ways. As a related example, the incentives of the person in the system are not wholly rational, right? And so, if you're trying to optimize my test performance, like if at some point I don't think I'm going to learn anymore, I might just start messing with the system or, answering randomly, doing things that like the system totally now mismodels me entirely.
Yes. Yep.
And these seem like really interesting questions to be able to sort of try and unpack.
Yeah, so I think also a lot of the things, another point that you just brought up here is that these systems are generally thinking of the person as kind of a black box and also but a sort of a unassuming black box, not an active box. And they could be adversarial, they could be cooperative, and that should change things in terms of how we teach and how we interact. And there's certainly been a lot of work on gaming the system and how people game or exploit features of the RL systems. But I think there's been less work on looking at the cooperative setting, like I want to learn this, you want me to learn this, can I need way less data if I can reason about the agent actively choosing examples?
Well, it seems like in the same way that you were articulating a shift toward almost like an open world assumption of action space, I'm sort of thinking about open world assumptions in, not sure if the objective is or the reward function is the right way to think of it, or what's in the actor, right? That there are sort of unobserved things about the actor, or that their strategy might shift. Like, I don't know how much. At some point, your model is just too unbounded.
Yes, exactly. And so sort of figuring out which of those parts of the key features to be doing optimization over or to consider in terms of robustness. Yeah. One big thing we've been trying to think about is robustness to failure of your model. That whatever model we use is going to be limited. And so how can we try to reason about that and be robust?
I'm wondering how you think about bias in your data set, especially in education, maybe in the context of institutionalized racism or bias of teachers, where certain classes of students have not been encouraged or have had high expectations, so they haven't tried, for instance, more advanced problems because they weren't provided to them. So how do you deal with that?
Yeah, I think that's a super interesting issue. So in these cases, we have not been addressing it. In some of our other work, if you know what some of those variables might be that you want to actively correct against, we have developed algorithms for how to do that. So in kind of more of a machine learning, supervised learning case, we've looked at, let's say, for predicting entrance to college, can we systematically make sure that you don't systematically overpredict for one group and underpredict for another group? And if you know what those sort of things are that you want to try to protect against, then you can put it in the system and you can make sure your solution respects that and solves for that. I think one very big challenge still is what if there are latent ones that are either correlated with that you don't realize, or if there are features that you're like, oh, in retrospect, I should have included religion, or I should have controlled for X, that you miss. And then your system will tend to exploit that information that might be sort of indirectly related to zip code or something like that. So I think that's a really big challenge in machine learning right now.
How do you deal with the change in the preferences from the actual user over time? Like at the beginning, they might want to learn something, or they desire to learn, and then at some point they may change. And many times, as Michael said, it's irrational, just because fashion changes, just because people get bored or tired. How do you deal with the complexity of the irrationality of a human being over time?
Well, we certainly don't completely. I think the issue of non-stationarity is super interesting. We had a paper recently looking at how do you detect that. So how do you detect when the system has changed? And related to that, Steve Collins and I are starting a new collaboration. He's in mechanical engineering, where he has an exoskeleton, and you're trying to optimize the parameters of the exoskeleton for a person. And one of the really interesting things is that it can take people a while to learn how to wear an exoskeleton. And so they're non-stationary during that time period. And then after that, you're kind of teaching them, this is what is exoskeleton, this is how to change your gait. And after that, you want to optimize the parameters for that person. And so we're trying to look at how can you tell when sort of the system is non-stationary versus when it's converged, and can you detect those changes? So I think it's a really interesting issue, and that often people will be changing those over time. Maybe they enroll in a MOOC and they're just going to learn a little bit of art history, and then they decide they love it. And so now they've changed it. And in some cases you can ask. Sometimes I think it's fully observable, or it's worth asking. And in other cases it might be harder to ask. And so you might want to say, hey, it seems like things have changed, like your pattern of behavior has changed. And that comes up in like dropout predictors too. So there's some work on that to try to detect it, but they're not always modeling all the dynamics.
I'm wondering, what do you see as the future of these learning systems? Is it always going to be a supplement to the kind of traditional system that we have, or is it at some point going to be like a standalone, everyone learns from their personalized system?
I think it's very unlikely that universities or sort of like collective learning institutions will go away, because I think there's a lot of other aspects that come right now from like the social interactions, and so I think it's doubtful that people will just be interacting like with their own tablet that's their like learning coach forever. But I think they could have a much larger role, and particularly in lifelong learning. I think that particularly with AI automation, I think people are going to need to do a lot more lifelong training. And I think having sort of a personalized coach that comes with you along that journey could be way more effective than the types of ways we do education right now. Like right now, so Nikki Couture, Jeff Biggin, and I had, who are professors at HCI and CMU, had a project a couple years ago called the Question Rater, with the idea being, if I want to learn a new topic, there's kind of no nice middle ground. Either I could just like start with like a course which assumes no background, or I have these really high cost ones of like bugging my colleague to sit down with me for 3 hours and teach me. And that if I just do a web search, there's no personalization of my background knowledge. And how would we create a system that could create a personalized tutoring system for me? And I think that sort of stuff is stuff that we could reach, that we could start being able to dynamically select material that says, okay, Emma knows something about optimization and reinforcement learning, so this is the type of material I should give to her for learning new things.
Follow up is,
last question.
do you think we're like too focused on trying to like really design for success, and we should be working more on design for failure? Like when these algorithms fail, should we then use that as an opportunity to infer something new about the user, maybe through interaction? Just saying the computer can say like, I have no freaking idea. What should I do now? Like, why don't you tell me what to do? As opposed to like trying always to be right.
Yeah, that's an interesting question. So can the system sort of figure out when it doesn't know and then maybe just, reach out to a human or reach out for augmentation? I think that's a really interesting question. I think there's cases we could do that. I guess I'll just say I thought you were going to go in a different direction, which is, should we be optimization for student success? Like, should that be the objective? And I have a lot of thoughts about that. And I think one of the new areas that I'm really excited about is trying to optimize not things like which activity to give, but try to decide things like metacognitive strategies, or do things like mindset interventions or imposter syndrome or belonging interventions, which from some of the psychologists here at Stanford have shown to have enormous implications. And they're really, really cool interventions because they have these recursive effects that if you give people different theories of how they can interpret their own experiences, then that can have huge recursive effects on how they can take advantage of opportunities. And so I think if we can put those inside of tutoring systems, both we could personalize those and we could scale up their impact. And so I'm much more excited about those these days rather than figuring out, video then problem or problem then video.
And if you'd like to interact more with Emma, she's around. You can take her courses on reinforcement learning and other kinds of cool things. You can go work with her on research. You can collaborate with her on research. Or you can swing by her office hours and just chat about cool things.
Thanks, everybody.
Thanks, Emma.